Okay. Now, you may feel like, dang, that's awesome. I rock. I can do iteration. You can do iteration. You have to do MATLAB. Just put the stuff in. Go. Let's do this. Let's do another set of equations. You ready? Here's my second set of equations. Negative 2x plus y plus 5z equals 15. 4x minus 8y plus z is equal to minus 21. 4x minus z plus z. Whoa! It's the same set of equations, except I flipped the first and last row, right? If you look at what I had there, I just flipped rows. So what do you think my answer is going to be? It should be 2, 4, 3, right? Dang. But I flipped things. And now what I'm going to do the same thing I did before. From the first equation, solve for x. From the second equations, solve for y. Third equation, solve for z. Okay. If you do that, let's solve for x here, right? I get if I solve for x, I get 15 minus, so I'm actually move the 2x over here, move the 15 over there. So it'll be minus 15 plus y plus 5z all over 2. From the second one, solve for y. In fact, if I solve for y, I get exactly what I had before. There it is. And from the third, when I solve for it, solve for z now, I get 7 minus 4x plus y. With that, I can make up an iteration scheme again. You just say, okay, how about I give an initial guess for x, y, and z, and iterate. Surely this will work again, because it worked before, and I know the answer is supposed to be 2, 4, 3. So let's go ahead and I'll do this again. In 19 iterations, I got pretty much down to numerical round off what the answer was, 2, 4, 3. And now let's just see what happens under this case. Okay, ready? After iteration 1. After iteration 2. Ooh, it's not looking so hot here. After iteration 3, 34, 8.01, negative 17. And that's kind of bad news. You just keep iterating and your numbers just blow up. What a letdown. I just showed you a super sweet way to just make up some equations, iterate, have this thing converge, and then I just showed you okay, take the standard set of equations, total failure. Now one of the problems, or one of the issues with computing is you never want to build a routine or a scheme that might work. This is usually frowned on. I think maybe I have the right answer, maybe, if this thing actually converged. Never, never, never did you do this. You just say, look, this sucks because that was cool, that's not so cool. Why did one work? Why did the other not work? Because if you're going to ever implement an iteration scheme, you have to be guaranteed that it's going to work for you. Okay? So we're going to talk about that. So these iteration schemes are called Jacobi iteration schemes. You take a solution, and you guess the next step of the solution, and your hope is that this thing converges to the solution. But you better know under what conditions this thing is guaranteed to converge, or else you never use this. Okay? All right. So I'm going to introduce you to the concept of what's called strict diagonal dominance. So I'm going to take this away. Shoot. I didn't want to erase that. I'll erase this. We'll come back. I'll have to rewrite those. It's all right. All right. Strict diagonal dominance. So let me define it for you. A matrix A is strictly diagonal dominant if the absolute value of every diagonal term is greater than, not greater than or equal to, but greater than the sum of the rest of the terms in that row. Okay? So you walk across all the columns except for the diagonal term. There you add up all their absolute values, and if for every diagonal element this thing is smaller than this, then it's said to be a strictly diagonal dominant matrix. Here's what's kind of awesome about strictly diagonal dominant matrices. If you have a strictly diagonal dominant matrix and you do this trick about rearranging things and doing the iteration scheme, if you have a strictly diagonal dominant matrix, then Jacobi iteration is guaranteed to converge for any guess. Rather remarkable, especially given what we know about Newton methods. Newton methods are guaranteed to converge provided you're sufficiently close. This just says no matter what, doesn't matter how bad a guesser you are, this thing will work for you. Okay? Should give you some confidence, right? That means this thing will always work for you, no matter how bad a guess you are. And, you know, it's awesome. It's a new technique, iteration to solution. So this is the theorem. And let's ask the following question. So what was the difference between the two problems we had? So let's talk about the first problem that I just erased. Let me write it back up. And here it is. It was 4x, the way I had written it, minus y plus z is equal to 7. And then this equation was 4x minus 8y plus z is equal to minus 21, and this was minus 2x. So I'm going to go here, and when I think about this and writing these three equations as ax equal to b, the matrix A associated with it looks like this. It is the coefficients of these things, so it's 4, negative 1, 1. Here it's 4, negative 8, 1, and then it's negative 2, 1, 5. And I ask the following question. If I write it this way, is that strictly diagonal dominant? So let's go down and check. Is 4 bigger than 2? Right? So remember, add the absolute value of every component. So the absolute value of 1 is 1, negative 1 is 1, plus 1, that's 2, that's 4. 4 is bigger than 2. So at least for this row, we're good. Right? Then I go down the diagonal and say, is 8 bigger than some of the other two terms? 8's bigger than 5. Sweet. Is 5 bigger than 3? Don't you love easy math questions? I could bring my daughters in here and say, is 5 bigger than 3? They'd be, yeah. Yeah, Daddy, it is. I'd be like, yeah, these girls are smart. Okay. All right. And here's the other thing. My 6-year-old, she's awesome because she asks a question like, Daddy, okay, what's 1,000,000,000 plus 1,000? 1,000,000,000, 1,000. She's like, oh, Daddy, you're good. As soon as she starts talking about multiplication, I'm in trouble, right? Because she'll be like, 1,000,000,000 plus 1,300. I'm like, oh, that's 1,000,000,000, 1,300. She thinks I'm just super fast, right? And as soon as she figures out to divide and multiply, then I'm toast. But she's 6. I got another little bit more time. It's just like they also think I can fix anything in the house. I can't fix much. I don't know. I don't have skills like that. But they think I do. So it's awesome. So You could say I'm deceiving them, but that's all right for right now. Let's not break the truth to them quite yet about their dad. Strictly diagonal dominant. Because of that, we rock that problem. Great. All right. Let's go to the other way we wrote it and ask the same question. Here is the second way we wrote this. Remember, this is just a rearrangement of that. And if we just think about what the matrix A would be here, -2, 1, 5. 4, -8, 1. 4, -1, 1. So we can go row by row. Is 2 bigger than 6? Nope. 8 is bigger than 5. 1 is not bigger than 5. So I fail in 2 of the rows. All I need to do is fail in 1. Okay? And then it's over. So this is why one worked, one didn't. So if you have a strictly diagonal dominant matrix, this is a way to solve the problem. Okay. So why would, yes?
So is it guaranteed not to converge, or just maybe it will maybe?
Oh, yeah, so, okay, so good question. All it means is you don't know. It might. It might for a good guess. It might for a bad, who knows? No guarantees. So the fact that you don't have a guarantee, you would never use it. Pretty much is what that means, in my view. Okay, so that's what we have for this and for guarantees about this thing. And it tells us clearly that how we should be thinking about setting this up. Now, what's important about all of this is the following. Why would we bring up another AX equal B technique? We have LU. We have Gaussian elimination. So we've got 2 techniques in place. This is the third, right? Just Jacobi iteration. And the reason we might bring it up is simply this. What is the operation count to perform this thing? It's all we're after here. In fact, iteration schemes such as these, when you start doing the iteration, play a huge role in modern computing. Because right now, the fastest schemes for solving what are called large sparse matrices. By the way, we already wrote down large sparse matrix in class. Remember when we discretized the Laplacian? It's a huge matrix if you do this thing, and only 9 diagonals matter. So it's sparse. Fastest way to solve sparse matrices right now, iterative techniques. Okay? When you're going to solve a million by a million matrix, the fastest way to get the solution of that AX equal B problem is going to be using a sparse solver. And the sparse solvers are all iterative techniques. And what the key is you want to try to guess a pretty good solution, and then it's going to iterate to the solution much quicker. Okay, so let's do an operation count. So let's go ahead and put these, let me rewrite this, and let's write what the iteration routine was. Okay. There. So this is kind of what we had as an iteration scheme that we built out of this thing. So let's count operations. What is the cost we have to pay for this AX equal to B method? Well, we have to update every single one of these components, right? There's n of them. Remember, that is at minimum what you have to pay for any scheme. Because you have to go and update every single of these components. It costs you n. That's the minimum. So now what else do we have to pay? Well, for each one of these, if you notice here, I've got to figure out, for my iteration scheme, how many things does it depend upon? How many of the terms here does it depend upon? Now, for this 3 by 3, it depended upon n of them. But remember, when we were solving, for instance, when we write that big Laplacian down, right, that's this huge, and 9 diagonals matter. And in fact, 9 diagonals matter, but for every term, how many neighbors do you have? Remember when we did the discretization? You depend upon your neighbors like this. 5 things. 5 things. Okay? So 5 things matter to you. So it's not n, it's how many ever diagonals are active. And you hope that number's small. So for instance, in our Laplacian operator, That was 5. That's very important. You don't want to put an n there. Because if you put an n there, you're at n squared already. So there's no way you're beating LU if you put an n there. But the fact is you got 5. So n times 5, which is less than n squared, as n's big. Okay? Times number of iterations. Call that k. So k will be your number of iterations. That's your operation count. This is why this is important in large sparse systems, because you get this to be a small number. And what you're hoping to do is get that to be a small number. Right? If these are both big, then this might be order n cubed. In fact, in the problem we have, you'll find that some of the methods we're using, we're not really using big enough matrices to make this thing beat the n log n speed of FFT. But where these techniques come in is when you're doing like, billions and size matrices. I mean, just huge, huge matrices, okay? And then you can win. So this is what you hope. The hope is that this thing here is less than n squared. Yeah?
LU decomposition is normally n squared,
Yep.
but for a sparse matrix, isn't it much, much less?
Well, it depends upon how the factorization happens. You have a sparse matrix, but the important thing is what does LU look like under the factorization. So an A matrix that's sparse doesn't necessarily generate LU matrices that are sparse. Does that make sense? Then it'd be order n squared, yep. But if you can get L and U to be sort of sparse, then you can still cut down further too, right? So all these techniques are what, by the way, if you want to spend a career doing this, this is what people do. This is what people do. There's a lot of people in scientific computing. This is all they do all day long is figure out how can I massage the system to get me that extra little bit. How do I get it down? Okay, I'm not n squared anymore. I'm n to the n times a half, right? You write a paper. You do a whole thesis on that. This is the trick. But in our case, all we care about is to say, here is an alternative technique for solving x equal to b. And the reason iterative methods become important is because there is the potential that you could beat things. Okay. So I've given you the most simple-minded iteration scheme possible.